Hi, I'm Greg Wagner, and I'm going to talk to you about my summer undergraduate research experience at the University of Michigan, which involves the numerical simulation of combustion in porous media. So before I talk about combustion in porous media, I want to talk about combustion in general, which involves the consumption of fuel. And one of these fuels that is used is natural gas. And this plot shows you that our consumption of natural gas is expected to rise about 50% in the next 25 years. Now, the consumption of natural gas, with this consumption, we are worried about scarcity of resources, as well as the emissions that naturally result from the use of natural gas, which is combustion. So these emissions that result from the combustion process mostly are produced by vehicles, but a significant amount involve the electric power generation and industrial processes. So when we talk about wanting to reduce emissions from combustion processes, we can try to improve conventional techniques. But these conventional techniques have been developed for 100 years approximately, and this is an incremental process that involves, slow improvements over time. Now, there are also new technologies which we can implement, which differ significantly from conventional techniques, but show significant improvement over these. And one of these technologies is porous media. So combustion in porous media over existing technology exhibits reduced emission of carbon monoxide and nitric oxide. It also can burn much lower fuel fractions than traditional techniques. So this means that we can use lower amounts of fuel and have a more controlled combustion process. It does this by recirculating heat from the combustion zone downstream to the reactants. So here are a few designs of porous media. You can see the flame is contained completely inside a porous matrix. So the flame inside the porous matrix heats up the solid, and then the solid then transports the heat downstream to the reactants before they are burned and preheats them. So these porous burner technologies, so you can see that on the left is a ring-type porous burner, which can be used for radiating heat for annealing or other metallurgical processes. And on the right, on the bottom right, there's a radiant-type porous burner, which is used for drying, which can be used to make paper or other things such as that. So as you saw from the previous slide, the flame is contained completely inside the porous media, which makes it very difficult to extract data. And this is why we need numerical models, that as well as other reasons. Also, the interaction between the combusting gas and porous solid is complex and difficult to understand. And from the limited experimental data, clearly this only exacerbates the problem. And numerical models, since you can have data anywhere you'd like, the physics of the combustion and heat transfer process can be understood a lot more quickly. Also, they're a lot more cost-effective than time-consuming and expensive experiments. The models can also be used to generate an advanced understanding of the interactions in the porous media, and this can hasten the development of porous burners. So there are lots of different models for combustion in porous media. These can range from complex, high-dimensional models, three-dimensional, direct numerical simulation models, to low-dimensional, simple, and efficient models, which involve a significant amount of assumptions. In this work, a lower dimensional approach is taken. This will contribute to an initial understanding of combustion and heat transfer properties in porous media, while still involving a significant complexity. Also, it can be completed in a summer, which is definitely important for a summer research project. So my goals for this research are to build a working model and a numerical scheme which will wrap around this model, and to undertake initial investigations of the effects of combustion chemistry, heat transfer, and fluid mechanics on the combustion process. So far, I have demonstrated promising results for a 1D flame simulation without the solid present. And so future work will couple this solid, the presence of the solid, with the combusting gas. So let me show you some initial results. So this is just a short video that I made. It may be difficult to understand just looking at these boxes, but this is a simulation of a flame propagating through the air. On the left-hand side, the top box is temperature distribution, and on the left-hand side, you can see it initializes at 300 Kelvin, which is about the temperature of the air that I'm standing in today. And on the right-hand side, it's about 2300 Kelvin, which is the temperature of the burned flame. So the slope in the temperature there is the actual flame itself, the increase in temperature that is involved in any flame. And the bottom is the species that are associated with this flame. There's only 5 species in this flame: methane, oxygen, nitrogen, carbon monoxide, and water. And so that's the simplified assumption that I'm using. But thank you for listening to my work today.